Okay, this will be the lecture for Chapter 12, and we'll be talking about solids. So first, going to start off by talking about solids, liquids, and gases, and how solids have a nice crystal structure. Introduce a new concept of density, which is going to be how much stuff is packed into a certain amount of space. Talk about elasticity, so how springs and rubber bands work. Talk a little bit about tension and compression, and why arches use compression and not tension. And just a little bit about scaling objects up. Since we will be talking about solids this lecture, liquids the following chapter, and gases the following, I just want to get some basic definitions out here. Now these are all states of matter, and the state does depend on temperature, and we'll talk about that when we talk about thermodynamics. So solids have a definite volume and a definite shape, right? If I've got a block right here, then it's got its own volume and its own shape. Maybe I can contort it a little bit, but it does generally return to its same shape. So I would say that it is not very compressible. Liquids have a definite volume, but not a definite shape, right? I can slosh water around in a glass. It doesn't have a definite shape, but it does have a definite volume. So I would say that liquids are also not compressible. That's why it hurts when you do a belly flop. In gases, there is no definite volume or a definite shape, right? We can fill up a balloon and we can wiggle it around, we can squish it, so the shape can kind of be anything that we want. And also it doesn't have a definite volume. It turns out the gases, you can compress them. So gases are compressible. Now, what do these guys look like on a molecular level? Well, if this is, I'm just going to say iron, and that's an iron atom, and that's an iron atom, and that's an iron atom. And these guys are kind of stacked together in like a nice, pretty crystalline structure where all of these iron atoms are joined together by some chemical bonds. Now, these guys are in motion. These guys are kind of wiggling back and forth. You can kind of think of these chemical bonds as being springs that allow this guy to bounce back and forth and transfer energy between one and the other. So there is definitely motion here. So these guys are in motion. They're wiggling back and forth. And that's why this thing is kind of solid. Now if we think about liquids, then I'm going to have some atoms here. My atoms are my blue blobs, and these guys are kind of loosely connected to other atoms in kind of long chains, if you will. And if we think about that, this guy can bend and fold and do whatever it wants. So that's kind of why this guy has a definite volume but not a definite shape. These chemical bonds are not nearly as strong, so there's not going to be as much energy in the chemical bonds as there is in a solid. And of course these guys are in motion as well. These chemical bonds act like springs, and so these guys are kind of wiggling back and forth, if you will. And lastly, for gas, we have individual molecules, and yes, they are in motion. And if these guys were in a container, these guys are kind of whizzing around the container. And kind of how fast they're whizzing around is going to depend on how hot they are, how much energy they have. So a gas that's really, really, really hot, the molecule is going to be whizzing quite a bit faster. Now, how do we know that solids are made up of this nice, pretty crystalline structure? Well, in about the 1920s, we were kind of playing around with X-rays, and what we kind of found is if you had a tube right here that generated X-rays, and you shine these X-rays through a slit and then into a solid material, that all the light's going to kind of splatter at very, very certain angles, and what it's kind of doing is it's diffracting or bending on this nice solid crystalline lattice. And if we had maybe a photographic plate or something that can detect X-rays on there, kind of what we see is this nice pretty pattern. And the nice pretty pattern tells us is that a solid is going to be a nice pretty crystalline structure. So let's take a look at a solid that we're pretty familiar with. Let's take a look at water. So water as a solid is going to be ice. Kind of take a look at a snowflake and you see the nice pretty crystalline structure. And kind of what's going on right here is this is actually ice in a crystal lattice, and it does look like a nice pretty structure. What we can kind of do is we can kind of treat these chemical bonds that you see right there as springs. So if this is a water molecule and this is one and this is one, These guys are in motion and they're connected by chemical bonds that act like springs, and these guys are kind of vibrating back and forth just like that because they do have some thermal energy, and I'll talk about that thermal energy in the next couple of chapters. What we want to keep in mind is that there is energy in these bonds, and for a solid there's a lot of energy in those bonds. If I want to break those bonds down, then it takes a lot of energy. Now, one new concept that I want to talk about is that of density, and all density is it's going to be the amount of mass per unit volume of a material. So if you think about having a solid material, some chemical bonds going on here, and the question is how close or how much mass do I have packed into the same amount of material? And really this is going to be an intrinsic property of each material. Every material is going to have a slightly different density because its crystalline lattice looks pretty much the same, and I kind of misspoke, I said crystalline lattice. This concept of density is going to apply for solids, for liquids, and for gases. Really it's how much mass is packed into some volume. Now the units of mass is going to be a kilogram, the unit of volume is going to be a cubic meter. So density is typically in kilograms per cubic meter. Your book seems to be overly fond of grams per centimeter, so it could be grams per centimeter. It's a mass per unit volume. And example would be the density of water. It's going to be 1,000 kilograms per cubic meter, or 1 gram per centimeter cubed. One thing I do want to mention before I go to the next slide is we can kind of shorthand this. The symbol for density is kind of a script looking P. It's called a rho. And so we would say density is equal to mass divided by volume, where the big V means volume and not velocity. So let's just do a quick little density calculation, and just to prove to you that we can do it for solids, liquids, or gases, let's figure out how much mass is in the room that you're in. And this is going to be, this is the density of air at roughly room temperature. But we know that density is equal to mass divided by volume. So if I want mass on one side, I need to multiply this side by volume and this side by volume, and those volumes are going to cancel out. So that tells me that mass is going to be equal to density times volume. Now I kind of need the volume for this room. What's that going to be equal to? Well, volume is going to be equal to length times the width times the height. Now, I don't know about your room, but it looks to me like this one might be roughly 3 meters by 5 meters by 3 meters. So that's going to be equal to 45 cubic meters. So 1.25 times 45, which is equal to 56.25 kilograms. Now, kind of the funny thing is if you convert this to pounds, it's roughly 125 pounds. So believe it or not, there's actually quite a bit of air in this room. Density is occasionally expressed as weight density, where rather than saying that it's mass per unit volume, it's weight per unit volume. But since weight is just mass times gravity, so mass times gravity divided by volume, you could pretty easily convince yourself that the weight density is just going to be gravity times density, and this one is going to have a unit of newtons per cubic meter because we're talking about weights. I'm not overly fond of weight density myself, but I do mention it because I have a lab that uses weight density. So density is going to be an intrinsic property of pretty much every material. Every material is going to have a slightly different density, and really it's going to depend on how massive the atoms are and how closely they are spaced together. And it's going to be a property of the material itself. It's not going to be a property of the object. So for example, I could have a kilogram of steel, and I could have 100 kilograms of steel, or actually I should say iron to make it a pure element. Then both of these guys are going to have the same density, and that density is going to be the density of steel, and it's going to be the same for this one or this one. It doesn't matter how much we have or even how we shape it. It's not going to be a property of an object. So if I had an aluminum can and then I went ahead and I crushed that aluminum can, I have not changed the density of the aluminum. The density of aluminum is still the density of aluminum. Now, the density of the can, the density of the object is very, very, very different than the density of the material. So here I've gone ahead and I've decreased the volume. So what I've done is I've made this can more dense and I've made the object more dense, but I have not changed the property of the material itself. Steel ships kind of use this same thing, right? If we have some body of water and we filled this thing up to the rim and we went ahead and we put a ship in there, and this ship is able to float. Why? Well, because there's a lot of air in there. Steel has whatever density it has. Now the object is going to be very, very, very different. So we fill up this object with a bunch of air and it can float on water because the object has a lower density than water. So let's just get a little bit of practice. What is the density of 1,000 kilograms of water, knowing that the density of fresh water is 1,000 kilograms per meter? Well, I would hope that you would write 1,000 kilograms per cubic meter. And if I asked you if this was 1 kilogram of water, would your answer change? The answer had better be no. What is the volume of 1,000 kilograms of water? Well, density is going to be equal to mass divided by volume. I want to isolate volume, so I'm going to multiply both sides by volume, and that's going to cancel those guys out. Now I want to get rid of the density, so go ahead and divide both sides by density, and that's going to cancel those guys out. And kind of what I'm left with is the volume is going to be equal to the mass divided by the density, so that's going to be 1,000 divided by 1,000. So the volume, so capital V, is going to be 1 cubic meter. Now, one thing that's kind of interesting is I said density is a property of the material, and some materials are really, really, really dense. Iridium is a great example. It's actually the second densest element, and this is the first most dense element, but no one's ever heard of that, so I really don't care too awful much. It's not too much denser than iridium, but what this means is iridium's got very, very, very dense atoms that are packed really close together, and it has a whopping density of about 22,500 kilograms per cubic meter, and you may have heard of it because it's used in spark plugs. Let's just go ahead and calculate real quick. The mass density is going to be equal to mass divided by volume. So if I multiply that side by volume and that side by volume, I can say that the mass is going to be the density times the volume, so 22,650 times 1, and that's 22,650 kilograms, which works out to be about 50,000 pounds or 25 tons. Mind you, this is 1 cubic meter, so 3 feet by 3 feet by 3 feet, so not a whole awful lot, and that's pretty heavy.